Hello, it has been a long time since the last lecture. Let's go through the questions in the last video. The first question is to solve an exact equation where we can check the exactness from partial m partial y equal to partial m partial x. To obtain the solution, just compute the integral m dx and n dy and compare them to retrieve the form of f, which is x psi y plus y. And using the initial condition, we have x psi y plus y equal to 0. The next question involves a non-exact equation, but we can use the formula mentioned in the last lecture to find an integrating factor 1 over x. After applying the factor, the calculation is similar to the first problem, and the solution is y lateral log x equal to a constant c. The third one is a Bologna equation with n equal to 3. So we can let z equal to 1 over y squared and rewrite the equation in z. Then we have the standard form here. And we can find the integrating factor as e to negative x squared. The remaining steps are straightforward, and the solution is y equal to 1 over square root x squared plus 1. The fourth problem is about population growth. We apply separation of variables and use partial fraction to rewrite the integrand. Subsequent steps are routine integration and algebra. This form of model is known as the logistic model, and in this case, the fastest rate of growth occurs when the population is half of the maximum capacity. Here is a plot showing how the population evolves, and a reference to logistic function in form of 1 over 1 plus e to negative t. The fifth one is an atmospheric science example of hydrostatic balance, starting from dp dz equal to negative g over r Tp, and a temperature profile of T equal to T log minus gamma z. We use that separation of variables again and integration with the appropriate boundary condition where at z equal to 0, the pressure is equal to some reference sea level pressure P log. The solution form is P equal to P log times T log minus gamma z over T log and to the power of G over R gamma. The pressure falls faster with height compared to an isothermal atmosphere, as colder layers above are thinner. So now let's get into the third lecture. Today we are going to talk about constant coefficient, homogeneous second-order ODE, and its variant, Euler's equation. In the last two lectures, we focused on the first-order ODE. Now it's time to move one order higher and deal with second-order ODEs. The simplest case would have constant coefficients, and the right-hand side is 0. We can have some inspiration from solving first-order ODE. Remember, if we have to solve dy dx plus ky equals 0, it can be solved by using a solution form e to rx, where r equal to minus k. So we can think about if e to rx also applies in the second order ODE case. If we plug in this test solution, dy dx equal to r e to rx, d square y dx square equal to r square e to rx, then substitution would yield the auxiliary equation, r squared plus alpha r plus beta equal to 0. This is a quadratic equation. As we know, from high school mathematics, we can have three situations: two real roots, one repeated real root, and no real root, aka two complex roots. The easiest scenario is two real roots. Denote them as R1 and R2. Then the two solutions would be y1 equal to e to r1x and y2 equal to e to r2x. Since the ODE is linear, by principle of superposition, if we have two solutions y1 and y2, then the linear combination c1y1 plus c2y2 is also a solution. This is shown below. y1 satisfies the equation, so we have this, and similar for y2. c1 times the first equation and c2 times the second equation, adding them up, we arrive at this, which shows that c1 y1 plus c2 y2 also satisfy the equation. The general solution would then be c1 er1x and c2 er2x. Now let's see an example. Solve d squared y dx squared minus 2 dy dx plus minus 3y equals to 0. The auxiliary equation is r squared minus 2r minus 3 equal to 0, and the roots can be seen as minus 1 and 3. So the general solution is y equal to c1 e negative x plus c2 e to 3x. There are two integration constants to be decided. The initial conditions have to give two pieces of information, so not only y, but dy dx at the starting point must also be given. If we continue in the last example, let's say y0 is 2 and dy dx 0 is 2. Dy dx can be computed as shown here, and some algebra after the substitution of x equal to 0, and these initial conditions show that c1 and c2 are both 1, and y equal to e to negative x plus e to 3x. The green curve and blue curve here represent the two terms contributing to the full solution, which is the red curve. The second case has one repeated root, and hence we only get one solution, e to rx, using the method. We need another solution which is linearly independent, such that it is not a constant multiple of e to rx. One potential educated guess is x e to rx. Substituting the second solution into the equation, where its first and second order derivative are displayed here. We have this. Notice that we can regroup the term, and the first term here is 0 due to the auxiliary equation requirement. The second term is also 0 due to r equal to negative alpha over 2 in the quadratic polynomial that has a single repeated root. So x e to rx causes the ODE to vanish, and therefore it's a valid solution. And the general solution would be y equal to c1 erx plus c2 x e to rx. An example is to solve dy squared d square y dx squared plus 4 dy dx plus 4y equal to 0, given an initial condition here. The auxiliary equation gives a repeated root of r equal to negative 2, and therefore the solution is y equal to c1 e to negative 2x plus c2 x e to negative 2x. If we match the initial condition below that, c1 has to be 2, and therefore after some algebra we also get c2 equal to 1. The full solution is then given by y equal to 2e to negative 2x plus x e to negative 2x. Here we show how the solution looks like as before. The green and blue curves give a rise to the full solution in the red curve. The most difficult case would be two complex roots when the discriminant of the auxiliary equation alpha squared minus 4 beta is negative. If we note the two complex roots as p plus minus qi, the solution would look like C1 EPX EIQX plus C2 EPX E negative IQX. However, since the original ODE start with real coefficients, we would want to rewrite the solution in real quantities. To deal with complex exponentials, we use Euler's formula, where EI theta is cosine theta plus I sine theta, and hence E plus minus IQX is cosine QX plus minus I sine QX. If a complex function yx satisfies the ODE that has real coefficient here, then isolating the real and imaginary parts, both of them will satisfy the ODE as two linearly independent solutions. Combining this and the Euler equations, we can lead to the conclusion there are two real value solutions, which is EPX cosine QX and EPX sine QX. An example is given here. To solve d squared y dx squared plus 2 dy dx plus 2y equals 0, the auxiliary equation r squared plus 2r plus 2 equals 0 has two complex roots, minus 1 plus minus I. So the two linearly independent solutions are e negative x cosine x and e negative x sine x. We can then use the form of y to compute dy dx and plugging in the initial conditions y0 equal to 2 and y prime 0 equal to negative 1. We know that the value of a will be 2 and the value of b will be 1, and the final solution is 2 e to negative x cosine x plus e negative x sine x. Here is a plot showing how the solution looks like. The green and blue curves decay exponentially and oscillate just as a sinusoidal function, and their sum gives the red curve as the desired solution curve. The last topic we touched today is Euler's equation that has the form x squared dx squared y dx squared plus alpha x dy dx plus beta y equal to 0. Compared to the second order constant coefficients ODE we just saw, we just add x squared before the second order derivative and x before the first order derivative. This can be solved by making a substitution z equal to lateral of x. By product rule, we can rewrite dy dx and d squared y dx squared as dy dz and d squared y dz squared, where after substitution, we arrive at a second order constant coefficient ODE with z as the independent variable. Another difference compared to the original second order constant coefficient ODE is that the new auxiliary equation has alpha replaced by alpha minus 1, and we can just solve using the method we have just discussed. Finally, we can recover the solution in terms of x by replacing z by lateral x. Here comes the last example today, which is to solve x squared dy squared dx squared plus 4x dy dx plus 2y equals 0. By making the substitution z equal to lateral x, we already know that the new auxiliary equation for y in terms of z is r squared plus 4 minus 1r plus 2 equal to r squared plus 3r plus 2 equal to 0. That has two real roots, r equal to negative 1 and negative 2. Yz is then c1e to negative z plus c2e to negative 2z. Transforming back to x by using z equal to lateral x leads to y equal to c1 over x plus c2 over x squared. These 4 questions are for take-home exercise. The first 3 problems correspond to the 3 scenarios seen in solving second-order constant coefficient ODE, and the last one is Euler's equation. Here comes the end of this lecture. Thanks for watching. If you like the content, please like and share and give comments freely.